Somewhere in the quiet air a few inches from your face, something is leaving you right now, streaming outward without sound, without weight, without any sense of effort, moving so quickly that the idea of speed almost stops meaning anything useful. It travels outward in every direction your skin faces, bounces off the walls of the room, brushes against the corners of furniture you can't quite see with your eyes closed, and some small fraction of it happens to strike a flat, smooth surface nearby before turning around and coming straight back to you, entering your eyes almost the instant it left, so quickly that the round trip feels like no trip at all. This happens continuously, thousands of times a second, a soft and endless conversation between your face and the room, and you have never had to think about it, because your eyes were built to catch the returning light and your brain was built to make sense of it, without asking permission first. Tonight, we're going to slow that whole quiet exchange down, not to rush toward an answer, but to sit with a question that has quietly bothered curious people for a very long time, long before anyone had the tools to explain it properly. The question is this: when you stand in front of a mirror, why does your reflection seem to swap your left hand for your right, but somehow leave your head still on top and your feet still on the bottom? Why does raising your right hand make the person in the glass raise what looks, to you, like their left hand, when nothing about up and down ever gets confused in the same way? It's a puzzle that seems almost too simple to be real, the kind of thing you might have first noticed as a child, tracing letters backward on a foggy bathroom mirror, watching your own handwriting turn strange and unreadable, and thinking, even before you had the words for it, that something odd was happening to the world in that glass. Let's start gently, the way the light itself starts, without hurrying to explanations yet. Picture a single point of light leaving your forehead. It doesn't know where it's going. It doesn't have a destination in mind, the way you might when you walk from a bedroom to a kitchen. It simply moves outward, in a straight line, until it meets something solid enough to interrupt it. When that something is an ordinary wall, painted in dull matte color, the light doesn't come back to you in any organized way. It scatters, bouncing off in 1,000 different directions, because the wall's surface, even though it looks smooth to your eye, is actually a landscape of tiny bumps and ridges when you get close enough. Each of those little imperfections sends the light off at its own private angle, and so what returns to your eyes from a plain wall is a scrambled, softened kind of glow, useful for seeing that the wall is there, but useless for seeing your own face reflected in it. Now picture that same point of light leaving your forehead again, but this time it happens to travel toward a different kind of surface, one that has been made deliberately flat and smooth, polished down to a scale so fine that the light can no longer tell the difference between one spot on it and the next. This is the surface we usually just call a mirror, though it's worth remembering that it wasn't always glass with a metal backing. For most of human history, people caught their own reflections in far humbler things: still water in a bowl or a pond, polished stone, sheets of hammered bronze or copper, carefully worked until the metal itself held a soft, dim likeness of whoever leaned over it. The Egyptians ground and polished metal discs for this purpose thousands of years ago, and later the Romans experimented with backing glass with metal to get a brighter, steadier image, though the results were still cloudy compared to what we take for granted now. Each of these surfaces, however different their materials, worked on exactly the same principle as your bathroom mirror tonight, because what matters isn't the substance, it's the smoothness. When a surface is smooth enough, every point of light that strikes it
bounces away at a very particular, very predictable angle, the same angle it arrived at, just flipped around an imaginary line perpendicular to the surface. Physicists have a plain, almost old-fashioned way of describing this, sometimes called the law of reflection, which says that the angle at which light comes in equals the angle at which it goes out. It's less a law in the sense of a courtroom rule, and more a law in the sense of something the universe simply, quietly, always does. Because that bounce is so consistent, so orderly, the light leaving different parts of your face doesn't get scrambled the way it does off a rough wall. The light from your left eyebrow bounces away, still carrying, in a sense, the information of having come from your left eyebrow, and it lands back in your actual eyes, still organized enough for your brain to reconstruct a face, your face, sitting there in the glass. The image feels immediate, obviously, since the whole round trip is happening at the speed of light, but there is a small and interesting delay if you like to think about it, more delay than you might guess, though far too tiny to ever notice in an ordinary room. Light crosses the space between your face and a bathroom mirror, and back again in a matter of nanoseconds, faster than any nerve in your body could register as a weight. So there you are, standing in front of the glass, and a face looks back that seems to be you, only somehow not quite you. This is where the puzzle usually announces itself. You lift your right hand to smooth your hair, and the person in the mirror appears to lift what your eyes immediately want to call their left hand. If you're wearing a shirt with writing on it, the letters look backward, reversed, unreadable at a glance in the way that used to make ambulance drivers, and mirror writers before them, spell out certain words in reverse on purpose, so that a driver glancing in a rearview mirror would see the word the right way around. And yet, curiously, your head is still on top in the reflection. Your feet are still on the bottom. Gravity, at least as your eyes report it, hasn't been touched at all. Only the sideways direction seems to have been quietly rearranged, as though some invisible hand reached into the glass and swapped east for west, while leaving north and south exactly where they were. This is the part that tends to trip people up, sometimes for years, sometimes for a whole lifetime without ever quite settling into a comfortable answer, because the natural first guess, the one most people reach for without thinking twice, is that mirrors have some special preference for left and right, some built-in bias that up and down simply don't share. It feels that way, it looks that way, and yet, and this is worth sitting with for a moment before we go any further tonight, that instinct turns out to be a little bit misleading, in a way that isn't obvious at all from just staring at your reflection. The mirror, it turns out, doesn't actually care about left, right, up, or down in any special way. It has no opinion on any direction lying flat along its surface. What it does, instead, is something quieter, something that has nothing to do with sideways at all, and everything to do with the one direction the light was actually traveling through, straight toward the glass and straight back again.
We're going to take our time getting there, the way you might take your time walking home, along a familiar street after dark, in no rush, noticing details you'd normally walk straight past. Before we return to that beam of light and follow it more carefully through its short, strange journey to the glass and back, it helps to sit for a while longer with the shape of the puzzle itself, to really feel out why left and right seem so easily swapped, while up and down never budge, because understanding why a question feels so persistently strange is often the surest way to loosen its grip, long before the answer itself ever arrives. Let's set up something steady to stand on, a kind of quiet scaffolding we can lean on for the rest of this journey through the glass. And the simplest way to build it is to imagine your own bedroom, the one you might actually be lying in right now, with 3 directions running through it like invisible threads. One thread runs up toward the ceiling and down toward the floor. Call that up and down, and notice how obvious, how unbothered, how thoroughly uncontroversial that direction feels. Another thread runs from the wall behind your head to the wall behind your feet, or if you're sitting up, from your back to whatever lies ahead of you. That's a second direction, and we'll come back to it, because it turns out to be the one doing all the quiet work tonight. And a third thread runs from your left side to your right side, out through one shoulder and out through the other, parallel to the floor, parallel to the mirror if you happen to be standing square in front of one. 3 directions, each one at right angles to the other 2, the way the corner of a room is built from 3 seams meeting in a single point. Architects and carpenters have relied on exactly this fact for thousands of years without ever needing to name it in words, because a stable box, a room you can trust to hold its shape, needs its walls meeting at right angles in 3 independent ways, not 2, not 4. This is nothing exotic. It's just the ordinary geometry of a room, the same geometry that lets you say a window is high on the wall, or low, or over to one side, or the other, without ever getting confused about what you mean. Now here's the first quiet observation, and it's worth letting it settle before moving on. A mirror, an ordinary flat mirror hanging on a wall or propped against a dresser, has a surface. That surface is flat, and being flat, it defines a plane, and that plane contains exactly 2 of our 3 directions. If the mirror is hanging on the wall behind your feet, so that you're facing it directly, then the surface of the mirror contains the up and down direction and the left and right direction. Both of those directions lie flat along the glass, sliding across its surface, the way your fingertip might trace a path across a tabletop without ever lifting off. The third direction, the one running from the wall behind your head to the wall the mirror is hanging on, doesn't lie along the glass at all. It pokes straight through it, perpendicular to the surface, the way a nail, driven straight into a wall, points directly into the plaster, rather than sliding along its face. This distinction, flat along the glass versus straight through the glass, turns out to matter enormously, though it doesn't announce itself as important at first. It just sits there, a simple geometric fact about how a flat surface relates to the space around it. But it's the seed of everything we're untangling tonight, so let's hold on to it gently and keep walking. Think for a moment about what it actually means to face a mirror. You turn your body so that your front points toward the glass. Your chest, your nose, the front of your feet, all of it oriented toward that flat surface, with your back turned toward the room behind you. In doing that, you've made a choice, though it rarely feels like a choice because it happens so automatically. You've aligned your own front-to-back direction with the mirror's perpendicular direction, the one poking straight through the glass like that nail into the wall. Your up and down direction, meanwhile, stays aligned with the room's up and down direction, because you're standing the way people generally stand, feet on the floor, head toward the ceiling. And your left and right direction lines up with whatever's left and right in the room. Your left hand, still on your left side, your right hand, still on your right side, at least until you look in the glass and start to wonder about it. Here's a small experiment you can run entirely in your mind, without needing to get up, without needing any mirror at all, just the quiet theater behind your closed eyes. Picture yourself lying on a bed with a large mirror mounted on the ceiling directly above you. An odd thing to have, perhaps, but useful for our purposes tonight. Now, the mirror isn't on the wall in front of your feet. It's up above,
parallel to the floor, and your front to back direction, the direction from your chest to your back, now lies flat along the mirror's surface, the same way your left and right direction usually does when facing a wall mirror. And what pokes straight through the ceiling mirror now, perpendicular to its surface, is your up and down direction, the direction from your head to your feet. If you imagine looking up into that ceiling mirror, something curious happens, and it happens precisely because the geometry has rotated along with you. In that reflection, your head and feet would appear swapped, the direction that used to feel untouchable, now behaving exactly the way left and right behaved a moment ago in the ordinary wall mirror. Your reflected feet would seem to be where your head is, hovering near the pillow, and your reflected head would seem to dangle near the foot of the bed. Meanwhile, your left and right, which used to feel so precarious in front of the wall mirror, would sit there calmly, completely unbothered, your left hand's reflection appearing exactly where you'd expect a left hand's reflection to be. Nothing about the mirror itself changed between these two situations. It's the same kind of flat, ordinary, perfectly unremarkable sheet of silvered glass either way. What changed was only your orientation relative to it, which direction of your body happened to be pointing straight into the glass rather than lying flat across its surface. The mirror was never playing favorites with left and right. It was simply doing the same thing it always does, reversing whichever direction runs perpendicular to it, straight in and straight back out, and leaving the other two directions, whichever two happen to be lying flat along its surface, completely alone. It's a bit like a narrow doorway that only lets you carry something through if you turn it a certain way. The doorway doesn't care whether you're carrying a broom, or a ladder, or a rolled-up rug. It only cares about the orientation of whatever's passing through it relative to the frame. Turn a couch on its side, and it slides through a doorway that would have refused it standing upright. The doorway itself never changes, only the relationship between the object and the opening. In the same way, the mirror never changes what it does, only which of your body's directions happens to be the one aligned with its single sensitive axis, the one running perpendicular to the glass. So the strangeness we started with tonight, the sense that mirrors have some special grudge against left and right, while leaving up and down untouched, begins to look less like a fact about mirrors and more like a fact about how we usually choose to stand in front of them. We almost always face a mirror the ordinary way, feet on the floor, front pointed at the glass, which means our front to back direction is almost always the one running perpendicular to the surface, and our left and right direction is almost always the one lying flat across it. Change that arrangement. Tip yourself sideways, lie beneath a mirror on the ceiling, and the so-called mystery moves to a different pair of directions entirely, because it was never really about left and right in the first place. It was about whichever direction happens to be pointing straight into the glass. That's the shape of the answer we're circling tonight, though we've only sketched its outline so far. The geometry of it, the bones beneath the skin. What we haven't done yet is follow the actual light, the beam that leaves your face, crosses the room, strikes the silvered glass and comes bouncing back into your waiting eyes, because it's in that short journey, that quiet bounce, where the real reversal happens, and where the picture we've just built will start to feel less like an abstract rule about planes and perpendiculars and more like something you can almost watch unfolding, slow and simple, right there in front of you.
Let's slow down for a moment and try a different kind of comparison, one that has nothing to do with glass or silver backing at all. Imagine you're standing in a quiet room, and instead of a mirror in front of you, there's another person. A friend, say, standing with their back to you, facing the same direction you are, both of you looking out toward the same far wall. At this moment, your friend's left hand and your left hand point the same way. Their right hand and your right hand point the same way too. You're aligned, like two people waiting for the same bus, both facing the same signpost. Now ask your friend to turn around and face you, not to step into a mirror, not to do anything optical at all, just to physically rotate their body the way anyone does 100 times a day, pivoting on their heels to greet someone who's walked into the room behind them. They turn, and now they're facing you. And here is the part worth sitting with, because it's the part that so many people quietly fold into their thinking about mirrors without ever noticing they've done it. When your friend turns to face you, their right hand is now on the same side as your left hand. Their left hand is now on the same side as your right hand. If you both raised your right hands to wave, the hands would be on opposite sides of the space between you. This is not a mystery. Nobody lies awake wondering why a person's hands swap sides when they turn around. It's the most unremarkable fact in the world. So unremarkable that we don't even notice we know it. If your friend is facing away from you and then spins around to face you, of course, their right side ends up on your left. That's simply what turning around does. Their body physically rotated 180 degrees around a vertical axis running through the top of their head down to their feet, and that rotation is what swapped which side is which, relative to you. Here's where the trouble begins. Gently, almost invisibly, when people try to explain mirrors, they often reach for this exact scenario as if it were the same thing. They picture themselves looking at their reflection, and they imagine that the person in the glass is like a friend who has turned around to face them, and so they assume the same explanation must apply, that the reflections, left and right, must have swapped for the same reason, because the person in the glass has, in some sense, turned to face them too. It feels like a satisfying explanation, because turning around really does swap left and right relative to an observer, and a reflection really does look like it's facing you. The two situations resemble each other on the surface, but they are not the same event, and the difference between them is exactly what we've been building toward tonight. Think about what actually happens when you turn to face a mirror versus what happens when your friend turns to face you. When your friend turns around, their body rotates. Their spine twists, their shoulders swing, their feet pivot on the floor. There is an actual, physical rotation happening in the room, a real turning of a real object through real space. That rotation is the entire cause of the left-right swap you observe. No rotation, no swap. If your friend could somehow face you without turning around, without any rotation at all, say by walking backward around you in a circle, while always keeping their back to the center, always facing outward, then when they ended up in front of you, nothing would have swapped, because nothing would have rotated relative to their own body. Now think about what happens when you stand in front of a mirror. Does your body rotate? No. You walk up to the glass facing forward, and you remain facing forward the entire time. There is no twist, no pivot, no spin, and you are not performing the maneuver your friend performed. And yet the image in the glass appears to face you, appears to have undergone whatever transformation would be needed to go from facing away to facing toward. This is the quiet substitution that trips people up. The reflection looks like the result of a turn, so the mind assumes a turn must have happened, and reaches for the explanation that fits a turn, the swapping of sides that comes from rotation. But nothing in the mirror rotated. The mirror performed a completely different operation, one we started sketching a moment ago, a flattening along a single axis, a front-to-back inversion, not a spin around a vertical line. It helps to picture the two processes side by side, almost like two different recipes that happen to produce a similarly shaped cake. One recipe is rotation. You take a body, you spin it around a vertical axis running head to foot, and after a half turn, its right side has swept around to where its left side used to be, relative to a fixed observer. That's your friend turning to greet you. The other recipe is reflection. You take a scene, and for every point in it, you build a corresponding point on the far side of a flat surface, at the same distance, along the single line running straight into that surface. No sweeping, no pivoting, just a point-for-point construction, straight back, straight through, straight out the other side, frozen there in the glass. That's the mirror. Both recipes end up producing something that appears to face the original. That's the coincidence that causes the confusion. A person who is turned around faces you. A reflection also faces you. Because both results share that one property, facing you, our minds quietly assume they must share their method too. And since we already know one method, the physical turn, we import its consequences, the left-right swap, onto the other, the reflection, even though the reflection got there by an entirely different route. There's a small experiment you can run in your own imagination right now, lying there in the dark, that makes this distinction easier to feel, rather than just think about. Picture yourself facing a mirror. Now picture, instead, a glass door, with someone standing just behind it, facing you, perfectly still, not moving at all. Line up the image in your mind, so the person behind the glass door is standing exactly where your reflection would stand. Same posture, same distance, arms in the same position. If that person did not walk around from behind you, if they never turned, if they simply happened to already be standing there, facing you from the start, would their right hand be on your right side or your left side? It would be on your left side. On the same side, your reflection's right hand appears to be. Nothing rotated to get them there. They were simply built, so to speak, facing you from the beginning, front to front, the way two people naturally end up when one is a mirrored construction of the other, rather than a rotated copy. This is the heart of tonight's untangling. The thread will keep pulling on as we go. A turned person and a reflected image can end up looking similar, both facing you, both seeming to present their opposite hand to your outstretched one. But they arrive at that resemblance through completely different physical stories. One story involves motion, a body sweeping through space, an actual half-circle traced by shoulders and hips. The other story involves no motion at all, just a geometric correspondence, a point here matched to a point there, laid out instantly and silently the moment light meets silvered glass. Confusing the two stories is almost irresistible, because our daily experience of facing another person is built entirely out of the first story, out of people walking, turning, pivoting to meet our gaze. We have so little daily experience of the second story, of something facing us without ever having turned, that when a mirror hands it to us,
We borrow the only explanation we have on hand, even though it doesn't quite fit. And once you can hold those two stories apart, gently, without letting them blur back together, something becomes possible that wasn't possible before, which is to actually watch the light itself do its quiet, patient work.
Let's slow down for a moment and look at something you probably have within arm's reach, even now, even in the dark. Somewhere near you, there is likely a shirt with a pocket on one side, a wristwatch worn on one wrist and not the other, a book with the spine on the left when it's closed and resting the way it usually rests. These are what we might call lopsided things, objects that are not the same on both sides, and they are going to help us more than almost anything else tonight, because lopsidedness is exactly what a mirror cannot hide. Think about a plain arrow, the kind you might doodle on a scrap of paper without thinking, a straight line with a little triangle at one end. Draw it pointing to the right. Now hold that paper up to a mirror. The arrow in the glass points to the left. Nothing mysterious happened here, nothing flipped in some deep cosmic sense, but the arrow's direction, which was the whole reason you drew a triangle on one end instead of just a plain line, has been reversed in the reflection. If you had drawn a plain line with no arrowhead, a perfectly symmetrical line, the mirror image would look exactly like the original, because there was nothing lopsided about it to begin with, nothing for the reflection to reveal as reversed. It's only once you introduce some asymmetry, some feature that breaks the tie between one end and the other, one side and the other, that the mirror has anything to show you at all. This is worth sitting with, because it's easy to rush past. A mirror does not reverse everything. A mirror reveals what was already capable of being reversed. Symmetrical things sail through a reflection completely unbothered. A perfect circle reflects as a perfect circle. A plain square reflects as a plain square. It's only the arrow, only the lopsided thing, that shows any sign of disturbance, and even then, we have to be careful about what kind of disturbance it actually is. Let's go back to that arrow, but this time, let's think about it the way a mirror actually thinks about it, which is to say, not by rotating anything, but by taking every point of the arrow and placing its twin at an equal distance on the other side of the glass. The tip of the arrowhead has a reflected twin. The tail of the arrow has a reflected twin. Every point along that straight shaft has its own twin, sitting directly across the glass from it, same height, same distance in, just mirrored, straight back out. If you trace this out carefully, point by point, you find that the arrow's overall left-right orientation, as drawn on the page, does indeed come out reversed in the image. But notice what did not happen. The arrow did not spin, the paper did not rotate. Nothing swept through space, the way a body sweeps through space when it turns to face you. The reversal came purely from that point-by-point correspondence, from the geometry of reflection itself, which treats depth, the direction pointing straight into the mirror, differently than it treats the directions running along the surface of the glass. Now let's bring in something even more telling than an arrow, because an arrow is drawn on paper, and paper is flat, and flat things can sometimes trick us into thinking the puzzle is simpler than it is. Let's use your own face instead. Imagine, just for tonight's purposes, a small dark mark on your left cheek, a little mole, or perhaps a smudge of something you touched without noticing. Whatever it is, it sits on the left side of your face as you experience your own face from the inside, which is also the left side as anyone standing in front of you would name it, since you're both agreeing to use your left, your actual anatomical left, as the reference. Now walk to the mirror and look. The mark now appears on the side of the reflection that lines up with your right hand.
If you lift your left hand, the hand on the same side as the mark, the reflection lifts a hand on the side that would be its right, if the reflection were a person you could shake hands with. This is the exact same phenomenon as the arrow, just wrapped in something far more personal, and personal is precisely why it unsettles people, in a way that a doodled arrow never quite manages to. We are used to thinking of our face as something other people simply look at and describe using their own left and right. If a friend tells you that you have a mark on your left cheek, they usually mean their own left as they face you, which corresponds to your right. The same crossing over that happens with handshakes and steering wheels. But when you look in the mirror, you are not being described by another person standing across from you. You are looking at a reflection of your own geometry, laid out point for point, and so the mark that sits on your own left, from your own point of view, appears in the reflection on the side that would be the right side of a person facing you. It is the same reversal as the arrow, just carried by skin instead of ink. Here is where it becomes useful to separate two different ways of talking about direction, because English, like most languages, blurs them together without warning, and that blurring is doing a lot of the confusing work tonight. There is object-centered direction, which means the left and right that belong to the object itself, built into it, the same no matter who's looking or from where. Your own left cheek is on your own left, full stop, regardless of whether anyone is watching, regardless of which way you happen to be facing. Then there is viewer-centered direction, which means the left and right that depend on where the observer is standing, the left and right of whoever is doing the looking. When your friend says you have a mark on your left cheek, they usually mean their own viewer-centered left, and because you're facing each other, their left lines up with your right.
Writing gives us another clean example of the same split, and it happens to be one that printers and sign makers have wrestled with for centuries, ever since the first ambulance had the word ambulance painted backward across its hood, so that drivers glancing in their rearview mirrors would see it the right way round, resolving into ordinary readable letters exactly when it mattered most. Painted normally, the word would come out mirrored in every rearview mirror on the road, letters flipped, order reversed, useless at a glance. Painted backward on purpose, it becomes readable exactly where it needs to be readable, in that small rectangle of reflected glass. This trick works precisely because the mirror does its point-by-point reversal reliably, every single time, and once you know the rule, you can write against it on purpose and let the glass undo your handiwork for you. Clothing gives us one more everyday texture to add to this pile of examples, something almost too ordinary to notice until tonight. A jacket with a zipper running up one particular side, a coat with buttons meant to be fastened by a right hand reaching across to a left flap. These garments are quietly asymmetrical in ways we stopped consciously registering long ago, the way you stop hearing a clock ticking in a familiar room. Look at such a jacket in a mirror, and the buttons appear to sit on the flap that would normally house the buttonholes, and the whole garment looks, for a moment, oddly unfamiliar, even though it hasn't changed in the slightest. The jacket is still exactly as it was when you put it down. Only the image has undergone that same faithful, patient, point-by-point correspondence, showing you a version of the jacket whose asymmetry has been carried across the glass and reported back to you with its left-right relationship, its object-centered handedness, reversed. So we now have a small collection of lopsided things, an arrow, a mark on a cheek, a word painted for ambulances, a jacket with its zipper on one side, and every one of them behaves the same way in front of a mirror, because every one of them has some feature that breaks the tie between its two sides. What none of them do
and this is worth holding on to gently as we drift further into tonight's subject, is rotate. Nothing about the mirror's relationship with any of these objects involves a turn, a spin, a body, moving through space the way a person moves when they pivot to face you. And if reflection isn't a rotation, then the natural next question, the one worth carrying quietly with you as your eyes grow heavier, is what exactly is happening to the light itself. In that instant it meets the silvered glass and bounces back out toward you, carrying all this careful, faithful reversal along with it.
Let's follow one single ray of light, just one, out of the uncountable multitude streaming from a lamp in your room, and see what happens to it the moment it touches a mirror's surface. This is easier to picture than it sounds, and it doesn't require any equations at all, just a kind of patient attention, the sort you might give to watching a ball bounce across a smooth floor. Picture the mirror lying flat, like the surface of a still pond at dawn, before any breeze has touched it. Now imagine a single, perfectly straight line rising up from that surface at a right angle, like a flagpole planted dead center in the pond, pointing straight up into the sky. This imaginary line has a name, and it is not a glamorous one. It is called the normal. That word doesn't mean ordinary in this context. It comes from an old habit among mathematicians and surveyors of using normal to mean perpendicular, standing at 90 degrees, to something else. So the normal, at any point on a mirror, is simply the invisible flagpole standing straight up from the glass at that exact spot, and every point on the mirror has its own normal, its own private flagpole, even though we usually only bother to draw one at a time, right where the action is happening. Now bring your ray of light in from some angle, arriving at the mirror the way a stone might arrive if you skipped it across that pond, coming in low and slanted rather than falling straight down. The ray approaches the flagpole from one side, and the angle it makes with that flagpole, measured from the pole itself rather than from the flat surface of the water, is called the angle of incidence. This distinction, measuring from the normal rather than from the surface, feels like a small technical fussiness, and in a sense it is, but it turns out to make the underlying rule far cleaner to state. So it has stuck around in physics classrooms for centuries now, ever since the earliest careful observers began writing these things down. And here is the rule itself, the entire law of reflection, so simple you could recite it in your sleep, which is more or less the point of learning it tonight. The ray that leaves the mirror, the outgoing ray, makes exactly the same angle with the normal, that same invisible flagpole, on the other side. If light comes in at a shallow, grazing angle, sneaking in low across the surface, it leaves at that same shallow, grazing angle, just mirrored, across the flagpole, to the opposite side. If it comes in steep, nearly straight down, almost parallel to the flagpole itself, it leaves almost straight back up, steep on the other side, retracing nearly the same path it came in on. The angle in equals the angle out, always, every single time, for every single ray, measured from that same perpendicular line. Nothing about the color of the light changes this. Nothing about how bright it is changes this. Nothing about the time of day changes this. It is, as far as anyone has ever been able to measure, one of the most reliable little facts in all of nature. There's something almost soothing in how unconditional this rule is. You don't have to know the material the mirror is made from, whether it's silvered glass hanging on a wall, or a sheet of polished metal, or, going back far enough in human history, a disc of bronze painstakingly ground and buffed by hand,
The kind wealthy households in ancient Egypt and later in Greece and Rome used to catch their own reflections before glass mirrors became common many centuries afterward. The law doesn't care. Angle in equals angle out, and it has cared this little, this consistently, for as long as light has been bouncing off smooth surfaces, which is to say, for as long as there has been light, and there have been smooth surfaces, long before anyone existed to write the rule down or give it a name. Now, one ray bouncing off one point is a tidy little fact, pleasant to picture, but it doesn't yet explain how you end up seeing an entire, coherent, detailed image of your own face, or a whole room reflected in a window at dusk. For that, you have to stop thinking about a single ray and start thinking, instead, about the almost incomprehensible number of rays involved in any ordinary act of seeing anything at all.
Your bedside lamp, or the last hint of daylight outside your window, is scattering light off every visible surface in the room, off your skin, your hair, the fabric of whatever you're resting against, and each tiny patch of each surface is sending rays outward in every direction at once. Not just one ray, but a whole spray of them, like the fine mist thrown up by a fountain. Some tiny fraction of that mist happens to travel toward the mirror. When it arrives, every single one of those countless rays obeys the very same law of reflection you just pictured with the single ray, and only in relation to the flagpole, standing at whatever specific point on the mirror that particular ray happens to strike. This is the part worth sitting with for a moment, because it's where the real magic of image formation quietly happens, without any magic at all. Two rays that leave from two slightly different points on your nose, say, one from the very tip and one from just a fraction of an inch to the left of the tip, arrive at the mirror at two slightly different points, and each obeys the law of reflection independently, each one bouncing off according to its own local flagpole. But because the mirror's surface is smooth, because every one of those tiny normals is standing at a consistent, predictable, unchanging angle relative to its neighbors, the two reflected rays leave the mirror still carrying, encoded in their new directions, the same spatial relationship they started with. The ray from the tip of your nose and the ray from just beside it don't get scrambled together, or swapped, or blurred into confusion. They stay distinguishable, still slightly apart from each other, still in the same relative arrangement, all the way to your eye. Multiply that by every point on your face, every point on your whole body, every point on the lamp and the wall and the ceiling behind you. Billions upon billions of individual points, each sending its own little spray of rays, each ray faithfully obeying that same unbending rule, and what arrives at your eye is not noise. It is an entire, coherent, point-for-point copy of the arrangement of light that left the room in the first place. That is what an image actually is, when you get down to the mechanics of it. Nothing more mysterious than an enormous number of individual, well-behaved bounces, each one boring and predictable on its own, adding up together into something that looks, to a tired mind at the end of a long day, like effortless magic. But this only works, this faithful preservation of shape and arrangement, because the mirror's surface is smooth on a scale far finer than the wavelength of visible light itself. Smoother than anything you could feel with your fingertips even if you ran them across it slowly in the dark. This particular, orderly kind of reflection has a name of its own, to set it apart from something far more common in the everyday world. It's called specular reflection, from the Latin word for mirror, speculum, the same root that gives us the word spectacles. And it stands in contrast to something called diffuse reflection, which is, if you stop to think about it, what almost every surface around you is doing at this very moment. Look at the wall of your room.
or the blanket pulled up near your chin, or the page of a book if you happen to be reading one before you closed your eyes tonight. Light bounces off all of these things too, obeying that same unbending law of reflection. Angle in equals angle out, at every single microscopic point. But the surfaces themselves are rough, riddled with tiny hills and valleys and fibers pointing in every conceivable direction, each one carrying its own tiny, differently tilted flagpole. So while each individual ray still obeys the law perfectly, faithfully, without exception, the rays as a whole scatter outward in a chaotic spray, headed toward every direction in the room at once, rather than toward one single, predictable direction. That's why you can see a wall from anywhere in a room, from any angle, while you can only see your reflection in a mirror from certain positions, standing in certain places relative to the glass. The wall gives you diffuse light, scattered in all directions, useful for seeing the wall itself, but useless for preserving anything like a coherent picture of the room. The mirror gives you specular light, orderly, directional, image-preserving, all because its surface stayed smooth enough for every tiny flagpole to point in exactly the same direction as every other one nearby. And once you have that distinction settled quietly in your mind, smooth and orderly, against rough and scattering, a curious question starts to surface almost on its own, one that will carry us gently into where this is all heading next.
Let's stay with that question for a while and let it lead us somewhere gentle. If a mirror is simply reflecting rays in an orderly way, each one bouncing off at the same angle it arrived, then why does it look like there's a whole other room back there, behind the glass, with another version of your bed and your ceiling and you, lying quietly in it? Nothing has actually gone through the mirror. No light has slipped past the silvered layer into some hidden chamber behind the wall, and yet the impression is so convincing, so spatially complete, that for as long as humans have gazed into still water or polished bronze or silvered glass, it has seemed entirely natural to speak of a reflection as being in a place, somewhere back there, at a certain depth behind the surface. Untangling why that happens, why your mind insists on placing an image at a distance behind the glass when nothing at all occupies that space, is really the heart of what a mirror does, and it comes down to how your eyes work and what they assume, more than anything happening in the glass itself. Think for a moment about how you actually see anything at all. Mirror or no mirror, light leaves a source, a lamp, the moon, a nightlight left on down the hall, and it strikes some object, a face, a coffee cup, the corner of a dresser. From every point on that object, light scatters outward in countless directions, diffusely, the way we were just talking about. Some small fraction of those scattered rays happens to travel toward your eyes. They pass through your cornea, through your lens, and they land on your retina, where your eye and brain together perform a small, practiced miracle they've been performing since the day you were born. They trace the rays backward, not consciously, not with any effort you're aware of, but automatically, instantly. Your visual system extends each incoming ray backward, in a straight line, as though the ray had traveled to your eye, without ever bending or bouncing off anything. Wherever those backward extended lines converge, that's where your brain places the object. That's where it seems to be. This works beautifully for ordinary seeing, because, for ordinary objects, the rays really did travel in a straight line from the object to your eye. The backward tracing matches the forward reality. The assumption holds. But now bring a mirror into the scene, and the assumption starts to work against the truth in a very particular, very orderly way.
Picture yourself lying in bed with a mirror across the room, propped against the far wall, catching a bit of moonlight or the soft glow of a nightlight. Light leaves your face, scatters in every direction, the way light always does, off a diffuse surface, and some of those scattered rays happen to travel toward the mirror. They strike the glass, and there, at the silvered surface, something orderly happens. Each ray obeys that unbending law we talked about, angle of incidence equal to angle of reflection, and bounces off in a new, entirely predictable direction. Some of those newly bounced rays then travel onward, across the room, and into your eyes. And your eyes, doing exactly what they always do, exactly what they've always done, trace those incoming rays backward, in a straight line, as if nothing eventful had happened to them along the way, as if they'd simply traveled undisturbed from their source.
But here's the quiet catch, the whole secret, tucked inside that automatic backward tracing. The rays entering your eyes did not travel in a straight line from your face. They bent, sharply, at the mirror's surface. So when your visual system extends them backward in a straight, uninterrupted line, ignoring that bend, ignoring that they ever touched glass at all, the backward lines don't lead to your actual face, sitting there in the room in front of the mirror. They pass straight through the mirror's surface and keep going, into the space behind the glass, into the wall, into whatever happens to be back there, plaster and wood and perhaps a stud or two, none of which has anything to do with what you're seeing. And it's precisely there, at the point where those backward extended lines finally converge, that your brain places the image, not because anything is there, not because any light has gone there, but because that's simply where the geometry of straight backward extension says it ought to be, given the assumption your visual system is built to make and cannot easily set aside. This is what's called a virtual image, and the word virtual is doing careful, precise work there, not the loose, casual work it does in so much modern conversation. It doesn't mean fake, exactly, or imaginary in the sense of make-believe. It means that no actual light rays converge at that location behind the mirror. If you could somehow slide a screen, a sheet of paper, or a piece of frosted glass into the space behind the mirror where the image appears to be, nothing would show up on it. No light is physically gathering there, the way it would gather to form a real image on a screen in front of a slide projector, or on the film inside an old camera, or on your retina itself. Compare that, for a moment, to a real image, the kind a lens can form when light rays genuinely do converge at a point in space, actually cross there, actually pile up their energy at that location, so that if you held up a card at just the right distance, an actual picture would bloom into visibility on its surface. A mirror image behind the glass offers no such thing. Slide your hand or a sheet of paper into that space, and you'd feel only wall, only plaster, only the ordinary solid world going about its business, utterly indifferent to the image your eyes insist is floating there. And yet the illusion, if we can even call something so lawful and so predictable an illusion, is remarkably precise, almost mathematically tidy in its behavior. The virtual image doesn't simply appear to float somewhere vaguely behind the glass, at some arbitrary depth chosen at random. It appears exactly as far behind the mirror's surface as the object sits in front of it. Step one careful pace closer to the mirror, and your reflection steps one equally careful pace closer to meet you, its motion mirrored perfectly in distance as well as in gesture. Step back, and it retreats by precisely the same amount, staying always at that same matched depth, an obedient, symmetrical partner behind the glass. This isn't a coincidence, and it isn't a rough approximation that happens to look right to a sleepy, undemanding eye.
It falls directly, inevitably, out of that same simple law of reflection we've been sitting with. Angle in equals angle out, applied patiently to every ray traveling from every point on your face, toward every point on the mirror's surface. Trace enough of those rays forward to the glass, and backward again, into the space behind it. Extend each one along its straight, uninterrupted path, and they all converge, every single one of them, at a point exactly as far behind the surface as your actual face is in front of it. The mathematics doesn't waver, it doesn't estimate. It arrives at that matched distance every single time, for every point on your face, which is precisely why the entire reflected image holds its shape, why your nose doesn't seem closer than your ears, why nothing about the reflection warps or stretches, unless the mirror itself is curved in some way that changes the geometry. So there you are, an ordinary person lying in an ordinary bed, and behind that flat pane of glass across the room sits an image of you, complete, symmetrical in its distance, matched pace for pace, to your every small movement, and entirely, thoroughly empty of any physical substance whatsoever. A place your eyes are certain holds something, built by nothing more than rays bouncing once off a smooth surface, and your own visual system's quiet, lifelong habit of tracing light backward in straight lines, without ever pausing to ask whether the light bent along the way. It's a strange kind of company to keep in a dark room, this faithful, placeless double, and it raises a next question almost as soon as you've settled into this one. A question about which way, exactly, that double is facing, and why it seems to face you at all.
Let's stay with that facing question for a moment, because it's the one that trips people up more than almost anything else about mirrors, and it deserves to be walked through slowly rather than answered too quickly. Hold up a page of handwriting to the mirror. The letters come back wrong. Not blurred, not dim, just wrong. Twisted into shapes that look like a child's attempt at a foreign alphabet. An E becomes something with its prongs on the other side. A word becomes unreadable, or readable only if you already know what it's supposed to say, and your mind does the correcting for you. This is usually the moment someone says the mirror flipped it left to right, and that phrase, comfortable as it feels, is where a lot of confusion quietly settles in and stays for years, because the mirror didn't touch left and right at all. It never does. What it did was much simpler and much stranger once you actually look at it. A mirror reverses front and back. That's the whole trick, the entire mechanism, nothing more exotic than that. Light traveling toward the glass gets sent straight back the way it came, reversed along that single axis, the one running perpendicular to the surface, the one connecting the front of an object to its back. Up and down are untouched. Side to side is untouched. Only the depth axis gets turned around. So why does the writing look left-right swapped instead of front-back swapped? Because of what you do with the page, not what the mirror does with the light. Think about how you actually hold that page up to a mirror. You don't hold it flat like a tray and tip it forward. You turn it around, the way you'd turn it to hand it to someone standing behind you, rotating it around the vertical axis, so the front of the page, the side with the ink, now faces the glass. In doing that turn yourself, with your own hands, you're the one who swapped left and right, because rotating something around a vertical line swaps its left and right sides while leaving up and down alone. The mirror then reverses front and back, exactly as it always does, and the combination of your rotation and the mirror's reversal is what produces that particular left-right jumbled look on the page. The mirror is innocent. Your wrist did it. Try it a different way, and the strangeness clears a little. Write a word on a transparency, something you can see through, and instead of turning it around to face the glass, tip it forward and down, keeping its left and right sides exactly where they were, laying it almost flat as you bring it toward the mirror's surface. Now, the reflection shows the word flipped, top to bottom instead, upside down rather than mirror written, letters standing on their heads instead of standing sideways. Same mirror, same law of reflection, same simple front-back reversal happening in the glass. What changed was only the way you carried the page toward it. The mirror has one fixed habit, turning front into back, and whatever axis you happen to rotate the object around on your way to the glass is the axis that ends up looking swapped to your eye afterward. Left and right feel special only because turning to face something, turning to face a mirror, a person, a doorway, is the most natural rotation a body performs. So it's the one we do without noticing, and then we blame the glass for a choice our own shoulders made. This is also why your reflections up and down stays so calm and unremarkable by comparison. You don't rotate your whole body around a horizontal axis to face a mirror. You'd have to do a strange sort of forward somersault to bring the top of your head where your chin usually is, and nobody does that just to check their reflection. Because that rotation never happens, the vertical direction in the mirror image tracks your actual vertical direction faithfully. Your head stays up, your feet stay down, nothing about height gets scrambled, the way left and right so often do on a printed page. The asymmetry isn't in the mirror. It's in the far more common habit of turning to face things rather than flipping over to face things. Floor mirrors and ceiling mirrors are useful for testing this a bit further because they force a different everyday habit into contact with the same unchanging rule. Picture an old-fashioned shop with a mirror laid flat on the floor near a shoe display, angled so customers could glance down and see how a pair looked from above, a fairly common fitting room fixture going back well over a century. Look down into it and your image appears beneath the floor, an upside-down figure standing on its head at the same depth below the surface as you stand above it, because the mirror still reverses only front and back, and in this orientation, front and back happen to run vertically, straight down toward the earth. Your reflection's feet meet your real feet at the glass, and from there, the rest of you extends downward into that imagined space below the floorboards, head pointing away from you, into the ground. Nothing about this contradicts anything said earlier. It's the same law. Angle in equals angle out. The same matched depth, just turned sideways relative to how a wall mirror usually presents itself, so it registers to a tired mind as a completely different phenomenon when it's really the identical rule wearing a different hat. A ceiling mirror does the reverse trick, sending your image up and away above you rather than down and away below, useful in certain shops and dressing rooms for checking the back of an outfit or the top of one's own head, a view almost nobody gets any other way, since human eyes were never built to look backward or straight up at their own scalp. And here, too, the reflection follows you with that same unwavering fidelity, matching your movements angle for angle, staying at a fixed distance
that mirrors your own distance from the glass, no matter that the whole arrangement is now stacked vertically instead of running out horizontally across a bedroom. Tilt an ordinary flat mirror, even slightly, and the picture inside it shifts in a way that can feel unsettling if you're not expecting it, though it obeys the very same rule throughout. Angle a hand mirror down a few degrees while looking into it from a fixed spot, and instead of seeing your own face, you might suddenly catch the ceiling, or your shoulder, or the far wall behind you, because the whole reflected scene rotates by twice the angle you tilted the glass. Tip the mirror 10 degrees, and the reflected world swings through 20. This is why the angle doubling shows up in things like periscopes and sextants, and why a slightly crooked mirror in an old house can throw a strangely angled slice of hallway into a bedroom, catching lamplight from a fixture nowhere near where the mirror itself is hanging, a small everyday puzzle with a perfectly tidy explanation sitting behind it. Curved mirrors bend the picture rather than merely reversing it, and that bending is where the story of mirrors starts branching out further than flat glass alone can take it. A mirror curved outward, bulging gently toward you the way the back of a spoon does, or the way certain convex safety mirrors do at the blind corners of parking garages and narrow shop aisles, shrinks whatever it reflects and widens the field of view, letting you see a much broader slice of a room from one glance than a flat mirror ever could, though everything within that broader view appears smaller and, at least near the edges, somewhat pulled and distorted from its true shape. A mirror curved inward, like the front of a spoon or a shaving mirror mounted for close work, magnifies instead, though only up to a certain distance, and past that same distance the image can flip upside down entirely, a shift that has confused a great many people leaning in a little too close to check their reflection in the morning.
And a segmented mirror, or two ordinary flat mirrors simply hinged together and angled toward each other, opens up something else again, a doubling and redoubling of reflections bouncing back and forth between the two surfaces, images of images stretching away into a kind of narrow, glowing corridor. Let's follow that hinge of two mirrors bouncing light back and forth for one more moment, because a camera does something related, though gentler, and it will carry us into a question that trips up almost everyone at some point in their life, which is why a selfie looks like one thing on the screen while you're taking it and a slightly different thing once it's saved. A simple front-facing camera, the kind built into a phone or a laptop, usually shows you a live preview that has been deliberately mirrored by the software, not by any glass or lens, just by a quiet instruction buried in the code that flips the image left to right before it ever reaches your eyes. The engineers who write that instruction do it on purpose, because a live, unmirrored feed from a front-facing camera feels wrong to almost everyone looking at it, the way your own reflection in a bathroom mirror feels natural, and a photograph of your own face feels ever so slightly foreign. When you move your right hand in a mirrored preview, the hand on the screen that matches your movement is the one on your left as you look at the screen, exactly as it would be in a bathroom mirror, and your brain, having spent an entire lifetime calibrated to that particular relationship between motion and reflection, relaxes into it without a second thought. It feels like looking into a mirror because the software has quietly arranged for it to behave like one. But here is the part that catches people off guard, and it is worth turning over slowly, the way you might turn over a stone to see what is underneath before setting it back down. The moment you press the shutter button, many phones save the photograph unmirrored, flipped back to how a stranger standing in front of you would actually have seen your face, which means The part in your hair that looked like it fell on the left while you were framing the shot can suddenly appear on the right once the picture lands in your gallery. Nothing about your face changed in that instant, and no additional mirror or lens was involved. What changed was only which version of the image, the live preview or the saved file, you happened to be looking at, and each version was built for a different purpose. The preview was built to feel like a mirror because that is what makes framing a shot feel intuitive, letting you nudge your head left when you want the image on screen to shift left. The saved photograph was built to show your face the way other people actually encounter it, the way it would look printed and handed across a table. Some camera apps let you choose which convention you prefer and save that as a setting, and some flip only the preview while leaving the raw sensor data untouched until export, and the exact behavior varies enough between phone models and software versions that it isn't worth memorizing any single rule as universal. What is worth carrying with you into sleep is the calmer, steadier fact underneath all of it, which is that no rotation happened at any point in that whole sequence, only a choice, made somewhere in a line of software, about whether to mirror the frame before showing it to you. Video calls sit in a similar spot, and they explain a small, specific unease that many people have felt without quite being able to name it. On most video call platforms, the little window showing your own face is mirrored, again for that same comfortable bathroom mirror feeling, letting you check your hair or your collar with the same intuitive left-right mapping you use every morning. But the image of you that is actually transmitted out to everyone else on the call is typically the unmirrored version, the one that shows your face as a stranger across a table would see it. So in a call with several people, you might be looking at a mirrored version of yourself in your own little box, while everyone else on the call is looking at the true, unmirrored version, and if you happen to glance at a shared screen recording afterward, your own face can look faintly unfamiliar in a way that's hard to place at first, before you remember that you had spent the whole call watching your mirror self rather than your camera self. Now, stepping away from screens entirely, there is the periscope, which does something wonderfully simple with the same tools we've already been turning over. A basic periscope is just two flat mirrors set parallel to each other, each tilted at 45 degrees, one up near the top of the tube and one down near the bottom, and light from whatever the top mirror sees bounces down the tube to the bottom mirror and then out to your eye. Because it uses two reflections rather than one, and because those two reflections are arranged symmetrically, a periscope hands you an image that is not mirror reversed at all, unlike a single flat mirror. Look through a periscope at a page of ordinary text, and the words read correctly, left to right, exactly as printed, which is part of why periscopes turned out to be so useful on submarines, letting a sailor read instrument markings or ship names on the horizon without having to mentally unflip anything first. Two reflections, each one a swap, cancel each other's swap out. The same quiet arithmetic we found earlier with two mirrors facing each other, just arranged this time to be genuinely useful rather than merely puzzling. Telescopes and microscopes bring in a different twist, and this is where it becomes important to hold apart, gently, the two very different things that can happen to an image, because it is easy for the mind to blur them together into one vague category called "the picture looks weird now." A simple refracting telescope, the kind built from two lenses rather than mirrors, typically produces an image that is upside down, not mirror reversed, but properly rotated by a full 180 degrees, top swapped with bottom,
and left swapped with right all at once, as a single continuous turn, rather than a flip. Astronomers mostly don't mind this at all, since up and down carry little meaning when you're looking at Saturn or a distant star cluster. Nothing in the sky insists on being viewed a particular way up. But telescopes meant for looking at earthly things, sometimes called terrestrial telescopes, add an extra lens or a small prism specifically to turn that upside-down image back the right way round, because nobody wants to watch a hawk fly upside down across a valley. A compound microscope does something similar to a simple refracting telescope, often producing images that are both upside down and mirror reversed together, which is why learning to move a slide correctly under a microscope takes actual practice. Nudge the slide left, expecting the image to drift left the way it would on a screen, and instead it drifts right, because you're now dealing with a full rotation layered on top of everything else, and your hands have to relearn, deliberately and a little clumsily at first, what left and right mean in that particular optical arrangement. And then there are corner reflectors, which behave almost like a magic trick once you understand the mirrors sitting behind them. Take 3 flat mirrors and join them at right angles, the way 3 walls meet in the corner of a room, floor, and 2 adjoining walls, and something remarkable happens to any light that wanders in. No matter what angle the light arrives from, it bounces off all 3 surfaces in turn and heads directly back out the way it came, parallel to its original path, almost as if the corner had simply reached out and redirected it home. This is why bicycle reflectors and the reflective paint on road signs work so reliably at night, sending your own headlights back toward your own eyes, regardless of the angle you're approaching from, and it's why astronauts left small corner reflector arrays on the surface of the moon during the Apollo missions, arrays still used today to bounce laser light back to observatories on Earth for measuring the moon's distance with remarkable precision.
3 mirrors, 3 reflections, and the strange geometry of odd numbers we touched on earlier all come together there in a single small glass fixture. Though what exactly happens to left and right after 3 bounces rather than 1 is a question worth sitting with slowly, the way you might turn a reflector over in your palm on a dark evening, feeling its faceted corner catch a street lamp before you glance up to notice how differently the same puzzle plays out on the still, patient surface of a pond. Let's think about gloves for a moment, because gloves are where this puzzle becomes something you can hold in your hands rather than just picture in your head. Take a left glove and a right glove. Lay them both palm down on a table in front of you and look at them carefully. They are, in every measurable way, identical. Same length of fingers, same curve of the thumb, same stitching, same leather, same everything, down to the smallest seam. And yet you cannot, no matter how you twist your wrist or rotate your arm, get the left glove to fit onto your right hand. You can slide it, flip it, turn it over, spin it in circles on the table, and it will never match. This is strange if you stop to really notice it, because almost everything else in ordinary life that shares identical measurements can be made to overlap. 2 identical coins can be stacked. 2 identical pieces of paper can be laid on top of each other so every edge lines up. But 2 gloves, mirror images of one another in shape, refuse this simple test. There is no rotation in ordinary 3-dimensional space that will turn one into the other. The only way to make a left glove look like a right glove is to reflect it, to run it through a mirror, and reflection is a fundamentally different kind of transformation than rotation, even though both can look, for a fleeting moment, like they're accomplishing the same thing. This property, this business of an object and its mirror image being unable to be superimposed, no matter how you turn them, has a name. Chemists and physicists call it chirality, borrowed from the Greek word for hand, because the hand is the most intuitive example anyone ever finds. A chiral object is one that differs from its own reflection in a way that can't be undone by rotation alone. A non-chiral object, sometimes called achiral, is one where the mirror image and the original can be rotated to match perfectly, the way a plane sphere or a symmetrical drinking glass looks the same as its reflection, no matter how you spin it. Your two hands are chiral, so is a corkscrew. So, it turns out, is a truly enormous share of the molecules that make up living things, and we'll come to that in a moment, but let's stay with the everyday objects a little longer first, because they make the abstract idea sit more comfortably in the mind before sleep. Picture a standard wood screw, the kind you'd find in a hardware drawer, tightened by turning it clockwise, the threads spiraling around the shaft in a particular direction, always the same direction on nearly every screw manufactured for the last couple of centuries in most parts of the world. If you looked at that screw in a mirror, its threads would appear to spiral the opposite way, and a mirror image screw, one that actually existed as an object rather than just an image, would need to be turned counterclockwise to drive it into wood. You could hold the real screw and its mirror reflection side by side, and they would look, at a glance, like the same object, same length, same diameter, same thread pitch. But pick them up and try to use them in the same screwdriver, turning the same direction, and one goes in while the other backs out. That spiral is chiral. It has a handedness. And once you start looking for spirals in the world, you notice they're almost everywhere, and almost all of them, at least among natural and manufactured screws in common use, twist the same way, which is itself a small historical accident worth pausing on, since there's nothing in the physics of screws that requires clockwise tightening. It simply became the convention that stuck. The way driving on the right or the left side of the road is a convention rather than a law of nature, arbitrary once, and then locked in by the sheer weight of everyone else already doing it that way. Now let's go smaller, down past the scale of hands and screws, into the world of molecules, because this is where chirality stops being a curiosity about gloves and starts explaining something genuinely important about how living things are built. Many molecules, especially the ones involved in biology, come in mirror image pairs called enantiomers, from a Greek root meaning opposite. Two enantiomers of the same molecule contain exactly the same atoms, connected in exactly the same pattern, the same bonds in the same lengths and the same angles. If you listed every measurable property of the two molecules individually, melting point, boiling point, density, the way they absorb ordinary light, you would find them identical in almost every respect. Yet they are, structurally, mirror images of one another, and just like the gloves, no amount of rotating one in space will turn it into the other. You have to reflect it, and reflection isn't something you can do to a physical object in three-dimensional space. It's a mathematical operation, not a physical one, at least not without passing the object through some higher dimensional looking glass that doesn't exist for us. So, the two enantiomers remain stubbornly, permanently distinct, two different objects that happen to share every measurement except their handedness. This might sound like a technicality, the kind of thing only a chemist would care about, except that biology cares about it enormously. The amino acids that build proteins in every living cell on Earth are,
with vanishingly rare exceptions, all left-handed, using the same kind of handedness language we've been using for gloves and screws. The sugars in your DNA, meanwhile, are almost all right-handed.
Nobody fully understands why life settled on this particular asymmetry rather than its mirror opposite, or its true origin in the deep history of the planet. And this remains a genuinely open question in origin of life research, one of those places where the honest answer is that scientists have compelling hypotheses but not a settled account, so it's worth resisting the temptation to think of it as solved. What is well understood is the consequence, which is that this molecular handedness matters enormously for how living systems function. A protein is a long chain of amino acids that folds into a very particular three-dimensional shape, the way a strand of beads might fold into a specific tangle, and that shape depends on the handedness of each link in the chain. Build the same chain out of the mirror image amino acids instead, and you'd get a different fold entirely, a shape that doesn't fit the locks it's supposed to fit. This becomes very concrete and very consequential in medicine. Some drug molecules are chiral, meaning they exist as left-handed and right-handed versions, and the human body, being built out of left-handed amino acids and right-handed sugars, is exquisitely sensitive to which version it encounters. Sometimes one enantiomer produces the desired medical effect, while its mirror twin does very little at all, essentially inert cargo along for the ride. In rarer and more troubling cases, the two enantiomers do genuinely different things in the body, one helpful, one harmful, which is part of what made the drug thalidomide, used in the late 1950s and early 1960s, such a devastating cautionary tale in pharmacology, a story that belongs to a longer conversation than we have room for here, but one worth knowing exists, because it's a vivid, sobering reminder that a molecule's mirror image is not a minor detail. It can be the entire difference between medicine and harm, all while every ordinary chemical measurement insists the two substances are the same. So what does the actual mirror have to do with all this? The flat piece of glass on your wall, rather than the abstract idea of a mirror image. A mirror takes an object and produces a version of it that has been flipped along the axis perpendicular to the mirror's surface. Front becomes back, while up stays up and side stays side, which is the same operation we worked through carefully in earlier sections. But here's the piece that connects it directly to chirality. That single flip is enough to convert a right-handed object into a left-handed one, or a left-handed object into a right-handed one, precisely because flipping one axis while leaving the other two alone reverses the overall sense of rotation, the underlying twist that defines handedness in the first place. Imagine your right hand held up in front of a mirror. The reflection shows what looks exactly like a left hand. Thumb where a left thumb's thumb would be, fingers curling the way a left hand's fingers curl. Nothing about the reflection is fuzzy or approximate. It is a perfect, faithful left hand, at least as an image. The trouble, the genuinely fascinating trouble, is that you can't reach through the glass and pick that image up and set it down on your left side to check whether it truly matches, because a flat piece of glass only shows you the image. It doesn't hand you back an object. If it could, if there really were some way to lift that reflected hand fully into the room as an object with real thickness and real bone and real skin, you would find it behaves exactly like an actual left hand, indistinguishable from one, and this is worth sitting with quietly for a moment before we move on, because it means the mirror isn't lying to you or playing a trick with light. It is showing you, with complete honesty, what a true left-handed version of your right hand would look like, down to the last crease in the knuckle, and the strangeness lives entirely in the fact that no rotation in the world you actually stand in
can turn one into the other. Only the mirror's particular kind of flip can do that. Which brings us naturally to a question about frames of reference, and what it actually means, mathematically as well as intuitively, for a coordinate system itself to flip.
Let's set the hand and mirror puzzle aside for a while and rest on something more physical, more textured, because before mirrors could show anyone a faithful left hand, someone had to make a surface capable of showing anything at all, and that turns out to be a much slower, much more human story than the geometry suggests. The earliest mirrors weren't glass, they were stone, and not just any stone, but obsidian, the black volcanic glass that forms when lava cools so quickly that its atoms don't have time to arrange themselves into crystals. Obsidian breaks with a smooth, almost liquid fracture, and if you polish that fracture patiently enough, rubbing it for hours against finer and finer abrasives, you get a surface flat enough to catch a dim, smoky reflection of a face. Archaeologists have found polished obsidian mirrors in Anatolia, in what's now Turkey, dating back roughly 8,000 years, which means people were staring at approximate versions of themselves long before they had writing, long before they had wheels, long before almost anything else we'd call technology. The reflection wasn't crisp. It was more like looking into a dark, still pond on an overcast day, a soft suggestion of a face rather than a portrait. But it was enough to notice something, that the reflection moved when you moved, that it seemed to live just behind the surface, and that touching the stone never let you touch the person looking back. Metal came next, and metal is really where the craft begins in earnest, because metal can be worked in a way stone can't. Ancient Egyptian mirrors were discs of polished copper, later bronze, mounted on handles often carved into the shape of a lotus or a papyrus stalk. The polishing itself was its own quiet discipline. A metalworker would grind the surface with abrasive sand, then finer sand, then perhaps ash or pumice, working in slow circular motions for what could be many hours, because copper tarnishes almost as fast as it's polished, and keeping that shine meant constant, patient maintenance. The Chinese were producing bronze mirrors by at least the Shang dynasty, more than 3,000 years ago, some cast with elaborate patterns on the back and smoothed to a reflective shine on the front, and by the Han dynasty, bronze mirror making had become genuinely sophisticated, with alloys tuned for reflectivity and backs inscribed with poetry, cosmological diagrams, animals representing the four directions. In the Mediterranean world, the Romans and Greeks worked with polished bronze, and for the wealthy, silver, which reflects light more efficiently than bronze, but tarnishes even faster, meaning a Roman mirror was less an object you owned once, and more an object you maintained continually, like a fire you had to keep tending. What's worth pausing on here, before we get sleepy and let the details blur, is how physically demanding this all was. There was no chemistry that could deposit a reflective layer in a controlled, repeatable way. Every mirror was the result of someone's arm, someone's patience, someone's sense, built up over years of practice, for when a surface had finally become flat enough and smooth enough to stop scattering light in all directions and start sending it back in one coherent, obedient direction. That's really the whole secret of a mirror. When you strip away the history, light needs a surface so smooth, relative to its own wavelength, that it reflects instead of scatters. Rough stone, or rough metal, bounces light every which way, the way a wrinkled bedsheet scatters a flashlight beam
into 100 dim patches. A polished surface aligns all those tiny bounces so they travel together coherently, and that coherence is what lets an image form instead of just a blur of brightness. Glass mirrors, the kind closer to what most of us picture, took a surprisingly long time to arrive, and even longer to arrive in a form that worked well. The Romans experimented with backing glass with metal, but their glass was thick, greenish, and full of small imperfections, so the reflections were dim and warped, more curiosity than tool. It wasn't until the medieval period, and then especially the Renaissance, that European glassmakers, particularly on the island of Murano near Venice, developed techniques for producing glass, clear and flat enough to be worth backing with metal at all. The Venetians used an amalgam of tin and mercury, a genuinely strange and hazardous process.
Sheets of tin foil were laid flat, mercury was poured over them, and the mercury would dissolve the tin's surface just enough to bond, forming a bright, silvery amalgam that clung to the back of a glass sheet pressed carefully on top. Excess mercury was squeezed out, weights were applied, and the whole assembly was left to cure for weeks. The result was the clearest, most faithful mirror the world had yet produced, and Venice guarded the technique so jealously that mirror makers who left the city to work elsewhere were, according to some accounts, threatened with serious consequences by the state, because a good mirror was, quite literally, a strategic economic asset. But mercury is a neurotoxin, and glassmakers who worked with it for years often suffered from tremors, from cognitive decline, from a whole cluster of symptoms, sometimes called Mad Hatter's syndrome, though that name is more associated with hat making, where mercury was used to treat felt. Mirror making carried its own similar toll, quietly, for centuries, and it wasn't until the mid-1800s that a German chemist named Justus von Liebig developed a much safer alternative, silvering glass using a chemical reaction, essentially precipitating a thin, even layer of pure silver directly onto glass from a silver nitrate solution. This is, remarkably, close to the same basic chemistry used in many mirrors today, or at least it was for the century or so after Liebig's discovery, and it meant mirrors could finally be produced without slowly poisoning the people who made them. Silver, though, has its own quiet flaw. It tarnishes, reacting with sulfur compounds in the air to form a thin, dark layer that dulls the reflection over years, which is why old mirrors often develop that smoky, spotted look near the edges, the silvering breaking down first where moisture can creep in behind the glass. So in the 20th century, particularly from the 1930s onward, a lot of mirror manufacturing shifted toward aluminum instead, deposited not through a wet chemical bath, but through a completely different process called vacuum deposition. In this technique, aluminum is heated in a vacuum chamber until it vaporizes, and that vapor drifts through the emptiness and settles onto the glass surface as an extraordinarily thin, even film, sometimes only a few hundred atoms thick. Aluminum reflects slightly less visible light than silver, a small difference most people would never notice in a bathroom mirror, but it resists tarnishing far better, and it can be deposited with remarkable precision and uniformity, which matters enormously once mirrors stop being about checking your reflection and start being about something more exacting. That's really
where the craft becomes something closer to a science of its own, because a bathroom mirror can tolerate small imperfections, tiny waves, and ripples in the glass that nobody notices because nobody's asking that mirror to do delicate work. But once you want a mirror to gather starlight, the tolerances change entirely. Astronomical mirrors, the kind sitting at the base of large reflecting telescopes, have to be ground and polished to a flatness, or more precisely, a curvature, so exact that the deviations are measured in fractions of the wavelength of light itself, sometimes down to a few nanometers across a surface that might span meters. The mirror at the heart of a large observatory telescope can take months or even years to grind, working through progressively finer abrasive compounds while constantly testing the surface with interference patterns, essentially watching how light waves bouncing off the glass interact with a known reference wave, because that interference pattern reveals bumps and dips too small to see or feel by hand, too small for almost any instrument except light itself. And once that shape is achieved, the mirror still needs its reflective coating, but here, the vacuum deposition has to be done with a precision far beyond ordinary manufacturing, because a coating, even slightly uneven, a few atoms thicker in one spot than another, could distort the image of a galaxy sitting billions of light years away, a galaxy so faint that it took months of the mirror faithfully gathering photons, one by one, to build a visible picture at all. There's something worth resting on in that thought before we move forward, that the same simple idea, a surface smooth enough to send light back coherently, connects a scrap of polished volcanic glass held up by someone 8,000 years ago to a mirror engineered today to catch the faint, ancient light of galaxies, and it's that same coherent reflection, however it's achieved, that eventually brings us back to the strange business of flipping, and to what a coordinate system is actually doing when we say it flips.
Let's rest for a moment on something that gets said so often about mirrors that it starts to feel true just from repetition, which is the claim that a mirror somehow knows the difference between left and right, that it reaches out and swaps your hands the way you'd swap two socks in a drawer. It doesn't. A mirror has no concept of left or right at all, no more than a pond has an opinion about which side of your face is which. What a mirror actually does, and only does, is reverse the direction of anything moving straight toward it and straight back, which physicists sometimes call reversing the front-to-back axis, the axis running from you to the glass and back to you again. Every point of light leaving your face travels forward, hits the surface, and bounces straight back along very nearly the same line it came in on. Nothing about that process touches your left side or your right side individually. The apparent swap you notice, the fact that when you raise your right hand, your reflection seems to raise its left, is not the mirror doing anything to your hands. It's a consequence of how you interpret the reversed depth axis once you mentally step into the reflection's position and imagine turning around to face the same way it does. You are the one performing the flip, inside your own head, in the act of making sense of what you're looking at. The mirror itself is indifferent. It reversed depth, only depth, and your mind translated that single reversal into what feels like a left-right swap because of the particular way human bodies are arranged, with a front and a back, and a habit of imagining ourselves rotating around a vertical line rather than tipping over like a pancake. If you did tip over instead of turning around, if you imagined bending forward at the waist to look at the world from your reflection's vantage, the way a diver arcs into a pool, the flip would seem to happen between up and down instead of left and right. The mirror never changes. Only the story your mind tells about it changes, depending on which imaginary rotation you use to place yourself in the reflection's shoes. There's a second misconception worth setting down gently, and it has to do with what the glass is actually doing while it holds your reflection. It can feel, especially late at night, with a dim room and a quiet mirror on the wall, as though the glass is holding something, keeping your image inside it the way a photograph keeps a face, or the way a pond might be imagined to remember the ripples that crossed it an hour before. But the mirror stores nothing. There is no image sitting inside the glass, waiting to be seen. What exists is a continuous, unbroken relay of light, arriving and leaving in a steady stream, over and over, many times each second, faster than the eye or the mind could ever separate into individual frames. The moment you step away from a mirror, whatever light was bouncing toward your former position simply continues on, uncaught, unremembered, into the room, and eventually gets absorbed by a wall, or a curtain, or the back of a chair, and that light carries no more information about your face at that point than the light that missed the mirror entirely and struck the wall on its own. Nothing is retained. Nothing is filed away. A mirror is closer to a hallway than to a drawer. Light passes through the space the mirror occupies, is redirected, and moves on, and the mirror itself is exactly as blank a second after you leave as it was a second before you arrived, holding no residue, no imprint, no accumulated memory of every face that has ever looked into it, of which, over centuries, in an old inherited mirror passed down through a family, there might have been thousands. A closely related question, one that surfaces sometimes in idle late-night thought, is whether the reflection you see is happening right now, instantly, or whether there's some lag, some delay between the moment the light leaves your face and the moment it returns to your eye after bouncing off the glass. And the honest answer is that there is a delay, though for a mirror on your bathroom wall, it is so vanishingly small that no human sense could ever register it. Light travels fast enough that crossing the arm's length of space between a face and a bathroom mirror and back again takes only a few billionths of a second, a span of time so brief that even the fastest nerve signal in the body, racing along at perhaps 100 meters per second, could not begin to notice it happened at all. But the principle underneath that near-instant reflection is the same principle that governs light, crossing far larger distances, and at those larger distances, the delay stops being trivial and starts being enormous. If a mirror the size of a small country could somehow be placed on the surface of the moon and aimed just right, the light bouncing off it and returning to Earth would take a little over 2.5 seconds round trip, because that's how long light takes to cross that particular gulf of space, out and back. This isn't just a thought experiment either. Reflectors really were left on the lunar surface, small arrays of corner-cube mirrors set down by astronauts and by uncrewed probes, and scientists on Earth have spent decades since bouncing laser pulses off them, timing the return with extraordinary precision, and using that timing to measure the distance to the moon down to a matter of centimeters, and to notice, patiently, year after year, that the moon is drifting away from the Earth by a small amount, something like the thickness of a fingernail, every single year. So reflection is never truly instantaneous. It only feels that way at the modest distances of daily life, where the delay is too small for any of our senses to catch. But the same physics stretches out, faithfully, across whatever distance light is asked to travel,
whether that's the width of a bathroom or the 250,000 miles to the moon and back.
There's another gentle misunderstanding worth clearing up here. This one about whether your reflection shows you what other people actually see when they look at your face. It doesn't. Not exactly. And the reason is simply geometry. When you look in a mirror, you are viewing your reflection from roughly the same angle you'd view another person standing in front of you, which means the reflected version has undergone that front-to-back reversal we already talked about. So any subtle asymmetries in your face, and nearly every face has them, a slightly higher eyebrow on one side, a faint tilt to the smile, are being shown to you flipped from how everyone else encounters them. This is part of why photographs of ourselves sometimes look faintly wrong in a way that's hard to name, a little unfamiliar despite being accurate, because most of us have spent far more hours looking at our mirrored self than at our photographed, unmirrored self, and the brain quietly comes to prefer the version it knows best, even though the version everyone else sees, the version your friends and family have looked at for years, is the other one, the one a camera captures, the one that was never flipped at all. And finally, before we let this thought settle, there's the strange pleasure of two mirrors facing each other, the kind of arrangement found in some barber shops and elevators and dressing rooms, where the reflection seems to repeat itself backward into what feels like infinity, a tunnel of smaller and smaller copies of the same room curving away into a soft green-tinted distance. It can feel almost supernatural, as though the mirrors are conjuring some separate, infinite space tucked behind the glass. But nothing is being conjured. Every one of those repeated images is simply one more bounce of the same light, traveling back and forth between the two surfaces, reflecting a few more times with each additional layer of depth, and losing a small amount of brightness at every bounce, because no mirror, however well made, reflects perfectly, which is why the copies fade gradually into a dim, greenish blur rather than continuing forever in sharp, endless detail. There is no infinite room. There is only a finite beam of light, doubling back on itself again and again inside a finite space, until it grows too faint to notice at all, and it's in that fading, in that gradual dimming of each successive image, that something else becomes visible about the nature of glass itself, something that has to do with color, and with why that dim tunnel always seems to drift toward green the deeper it goes. That drift toward green, if you ever find yourself wondering about it in a waiting room or a dressing room mirror, comes from the glass itself rather than from the silvered backing that does the actual reflecting. Ordinary glass is not perfectly colorless. It has the faintest tint of green in it, a trace left over from the iron impurities that occur naturally in the sand used to make it, and in a single pane, this tint is far too slight to notice. Light passes through so little glass, just the thickness of one sheet, that the green never has a chance to accumulate into something visible. But in two facing mirrors, the light is not passing through the glass once. It is passing through it dozens of times, back and forth, each pass adding one more whisper of green before the light bounces off the silver and travels through the glass again on its way back out. By the time an image has traveled deep enough into that tunnel to become one of the small, dim, distant copies, its light has crossed through so many layers of faintly tinted glass that the tint finally becomes visible, the way a single sheet of pale tissue paper looks almost white, but 100 sheets stacked together look distinctly colored. So the green is not a trick of infinity. It is simply glass being glass, many times over, and it is one of those small physical details that hides in plain sight until two mirrors happen to be arranged just right to reveal it. And now, with that small mystery quietly resolved, it feels like the right moment to come back to the room you started in, the dark, quiet room, and to the mirror that may or may not still be somewhere nearby in it, unseen in the darkness but still doing, in principle, exactly what it always does. Because after all of this, after color and brightness and infinite seeming tunnels of fading light, it's worth returning to the very first puzzle, the one that probably brought you into this whole, slow unwinding of thoughts in the first place. Why does a mirror seem to flip left and right, but never up and down? By now, you may already feel the answer settling into place on its own, the way a familiar tune settles into place before you can quite name it. But there is something calming about walking through it one final time, slowly, the way you might walk once more through a house before turning off the last light and heading to bed. A mirror does not flip anything left to right. It does not flip anything up and down either. It performs exactly one transformation, and it performs it in exactly one direction, the direction pointing straight into the glass and straight back out of it. If you are standing in front of a mirror and you imagine a perfectly straight arrow running from the tip of your nose forward into the glass, that arrow is the only thing the mirror reverses. Front becomes back. Whatever was closest to the mirror, like the tip of your nose, has its reflection projected as though it were now the farthest point, and whatever was farthest from the mirror, like the back of your head, has its reflection projected as though it were now the nearest point. That is the entire transformation. One axis, reversed. Nothing else touched at all. Up stays up, because gravity did not change, and neither did the mirror's orientation relative to the floor and ceiling. Left stays left, and right stays right too, in the strict, literal sense that the mirror never touches those directions. What actually happens is that your own mind takes this simple front-to-back reversal and translates it into something that feels, instead, like a left-right reversal. And it does this because of a very specific, very human habit of imagination that has nothing to do with optics and everything to do with how we understand other people's bodies. When you look at your reflection, you are not looking at a flat picture the way you might look at a photograph pinned to a wall. You are looking at something that resembles a person facing you, because it has two eyes and a nose and a mouth arranged the way a face is arranged, and your mind, without being asked, treats this arrangement the way it treats any person standing in front of you. And the way your mind understands another person facing you is by imagining, at least in some quiet, automatic corner of itself, what it would be like to swap places with them, to imagine that person turning around to stand shoulder to shoulder with you, both of you facing the same direction. Try to picture it slowly. Imagine a person standing directly across from you, close enough to shake hands, facing you. Now imagine that person rotating in place, turning around a vertical line running from the top of their head to the floor between their feet, spinning until their back faces you, and then continuing until they end up standing beside you, facing the same way you are facing. When a real person does this, when they physically rotate around that vertical axis to end up beside you, whatever was on their right hand, the hand nearer to you a moment ago before they turned, ends up on the same side as whatever is now nearer to you again after the turn, but their front and back have also been carried along with that same rotation, so their front is now pointing the same way as yours. Their whole body has turned as one rigid piece. But the mirror does not do this. The mirror never rotates anyone. It only reverses front and back, instantly, without any spinning at all, while leaving up, down, left, and right completely untouched. So when your mind compares what it's looking at, the mirror image with its front and back reversed but its left and right undisturbed, against the mental image of a person who has physically turned around, with their left and right swapped along with their front and back, the two pictures don't match on the left-right dimension, and it is that mismatch, that quiet failure of the comparison, that gets experienced as the mirror having flipped you left to right. The mirror did nothing of the kind. Your mind simply reached for the most natural explanation available to it, the explanation it uses every single day for understanding other people, the idea of someone turning to face the same way you do, and that explanation, useful as it almost always is, happens to be the wrong one for this particular situation, because a mirror reflection was never produced by anyone turning around at all. This is, in its own small way, a kind of optical illusion that isn't really about the eyes so much as about expectation, about the mind reaching for its most familiar tool, the tool built for making sense of other people's bodies and their movements through space, and applying that tool to something that only looks like a person but was actually made by an entirely different, much simpler process. Light bounced off you, struck a flat silvered surface, and bounced back at an equal and opposite angle, all in the time it takes light to do anything, which is to say, no time worth mentioning at all. No turning happened. No spinning happened. Only that one clean, quiet reversal of front and back, the depth of the world folded backward through the glass, like a page turned in on itself, while everything sideways and everything vertical stayed exactly, faithfully, precisely, where it had always been. There is something almost restful in realizing that a puzzle which has nagged at curious minds since antiquity, one that occupied Plato when he wrote about images and appearances, one that Lewis Carroll turned into a doorway for a girl to walk through into another world, one that still shows up in physics classrooms and casual arguments at dinner tables today, comes down in the end to something this simple: symmetry, and only one axis of it. The world folded once, along the line that runs straight out from the glass, and a mind so used to imagining other people turning to face it, that it quietly, harmlessly, mistakes that single fold for a much larger rearrangement than the one that actually took place. So if you find yourself near a mirror again sometime soon, in a bathroom at midnight, or a hallway half lit by a nightlight, you might notice, without needing to think hard about it anymore, that nothing sinister or strange is happening in the glass. Just light, arriving and returning, obedient to the plainest rules of geometry, indifferent to left and right, touching only the one direction that faces it, over and over, patiently, the same way it has every single time a mirror has ever been made, or held, or glanced into, quietly, without any need for you to understand it at all, in order for it to keep working exactly as it always has. Rest well.